I will click the magic button, and let's take attendance. Looks like I have angered my taskbar, and so it will not appear anymore. So please tell me that you're here, and we shall begin. So, an action-packed day for us today. We're going to talk about logic some more and get into arguments and things like that. It's going to be great. All right, so the first thing that I want to talk about is the difference between deduction and induction. You might have heard these terms before, like Sherlock Holmes, master of deduction, right? What does it all mean? Let's figure it out. So it turns out that deduction is something that computers are awesome at, very easy for them to do. But induction is pretty hard for a computer, but kind of natural for us humans, which is interesting to think about. Maybe one day they'll become smart enough to take over our powers of induction, but not yet. What's the difference? And so I'm going to be trying to answer for most of the slides today the question of what makes an argument correct? How do we know it's good? Okay, so let's first talk about deduction, because that's the easier of the two. It makes more sense, I think. So let's first talk about arguments themselves, right? If you're making an argument to somebody, you're trying to conclude something, right? That's what you're trying to convince somebody of. But you also have some premises that are helping you, right? The premises of your argument are the things that you're assuming in order to prove your conclusion, okay? That's what a premise means. It's just a fancy word for assumption. And so, yeah, that's an argument. I've got a bunch of premises, so assuming these premises are true, then my conclusion is true. That's what I'm trying to convince you of, okay? And we say that an argument is deductive when it's always true that the conclusion is true, right? When the conclusion is a certainty, we say, which is weird to think about. I'll give some examples and it will make more sense to you. But an argument is deductive when the conclusion is a certainty. Like if the premises all line up, then it just naturally follows that the conclusion must be true. That is a deductive argument, okay? So let me try and draw this with some clouds first. So here's my premise 1 that I'm using to help me. Here's my premise 2 that I'm using to help my argument, my conclusion. Here's my premise 3. And I'm using all of those to prove some kind of cloud that is a conclusion. Okay, that's the goal. So here's my conclusion. And all of these premises are helping it, giving it strength. And the conclusion must always be true in a deductive argument, if the premises are true. So here's an example, and hopefully it'll make sense now. So premise 1, it's sunny in Fresno. Seems to have started to become spring already, which is interesting. So that's fun. So it's sunny in Fresno. That's true today. That's premise 1. So assuming that, and assuming premise 2 as well. So if it's sunny in Fresno, then Lawton won't be carrying an umbrella. I did not bring one today, so that is also true, right? Those are my premises. And then I'm trying to conclude something. What am I arguing to you? And so the conclusion based on these premises is, so Lawton won't be carrying an umbrella today. These kind of link together and give us that conclusion. Okay? Any questions about that? It's like, based on these premises, it's a certainty that Lawton won't be carrying an umbrella. That is deduction in a nutshell. Does that make enough sense? Any questions about that? Because induction is, and so I think you can imagine that computers are really good at this, like, okay, line up the premises, see if we can conclude something, nothing could go wrong. Induction is something different. You may have, if you've taken like CSCI 26, you might have learned about mathematical induction. This is something completely different from that. Induction is an overloaded term, sadly. But this induction is all about probabilities. Well, that's the difference. Certainty versus probabilistic truth. Probabilities. So many I's. So we say that an argument is inductive when the conclusion based on the premises being true is just very likely. Not always true, but most of the time we can conclude. That's the kind of thing that humans are good at reasoning about, right? So here's an example inductive argument. Let's say that here's our one premise. So assuming this, I'm trying to prove this conclusion or argue this conclusion is true. So premise, assume that every time I've walked by that dog, it hasn't tried to bite me, okay? That is my premise. That's something I've assumed. I've noticed that based on empirical evidence or something. And so I'm concluding then that so the next time that I walk by that dog, he's probably not going to try and bite me based on my prior experience, right? Based on my premise. Obviously, maybe the dog could be having a very bad day and will end up biting me. It is not certain that this conclusion is true based on the premise, okay? But probabilistically, it's very likely. That's the difference between induction and deduction. Is that good enough? Any questions about that? That's the key. And so this is a bit harder to program a computer to understand inductive arguments because, oh man, do you have to suddenly start reasoning like a human might based on probabilities. Okay? So that's the first bit of all this. Let's move on to a different topic, if we're okay. Any questions before I switch gears into something different? New terms? All right, so let's talk about something called validity and soundness. Okay? And I'll try and answer this question. How can I attack an argument in a logical way? And by the way, validity and soundness, they kind of go hand in hand. Soundness is strictly stronger than validity. Well, I'll define all these terms, but stronger. Just S for stronger than validity. All right, so let's learn how to attack arguments and see if they're correct. Okay, so we say that an argument is valid, one that you're trying to make. It's valid if it's impossible for the premises to be true and the conclusion to be false. Okay, that's what's called a valid argument. If those premises are true, then it must be the case that the conclusion is also true. Kind of like what it means to be a good deductive argument, right? Validity. An argument is valid if it's impossible for the premises to be true and the conclusion to be false. Again, I'll give you plenty of examples and this will make more sense. So that's valid, validity. And then we have sound. So soundness. An argument is sound if it's valid. So it has to like check this box. And also all of the premises are true. Because maybe some of those premises aren't always true. Doesn't matter in terms of validity, but for soundness, that's a stronger notion. And the premises have to be true in order for an argument to be sound. Okay? So here is like the thing that you would learn about in a philosophy class if they taught you these two terms. So the quintessential sound argument that everybody likes to give. Here are my two premises, 1 and 2. And here's my conclusion, 3, let's say. And so there's kind of like a line between them. The things I'm assuming and the thing I'm trying to prove based on the assumptions. And so here are my premises. All men are mortal, assume that. And then Socrates is a man, assume that too. And then conclude, therefore, Socrates is mortal, right? First of all, this is valid because do you see how both of these lead to Socrates being mortal? Like, all men are mortal, Socrates is a man. Plug him into that, kind of. And then you get out that Socrates is mortal, yeah? That means it's valid. It's impossible for this to be false, since we're assuming these premises to be true. And then it's also sound because these are true premises, right? All men really are mortal. We haven't created like some sort of man that lives forever yet, unless like vampires exist or something. Who knows? But for all we know, men are mortal. And Socrates, pretty sure he was also a man, okay? So the premises are true, and also we saw that it was a valid argument, okay? So that's what it means to be sound. And sound is stronger than validity because here is an argument that is valid, but it is unsound. So again, you have premises and the thing you're trying to conclude. So like 1, 2, 3. All right, so here's the argument. Everyone who watched Hamilton enjoyed it. All right, so assume that. And then assume that John watched Hamilton, right? Kind of like this argument all over again. Plug John into statement 1, and you can conclude that John must have enjoyed Hamilton, right? Based on those assumptions. And so it's totally valid. Like, assuming these, you can totally prove that John must have enjoyed Hamilton. But sadly, some people in the world didn't like it when they watched it, right? So this is probably a true statement. We know that John watched Hamilton, but this one right here is false, right? Some people who watched Hamilton did not enjoy it, right? So that kind of ruins the day and it makes it an unsound argument. But it's still valid. You see how these premises, if they were true, pigs could fly, then you can get our conclusion. It follows. It's correct. It's valid, but it's not sound. Okay? Premises aren't all true. Does that difference make enough sense to us? That's the key difference there. All right, let's try an example before I give you a bunch to try yourself. Okay, so let's see. Is the following argument valid or sound? Okay, so there's always a therefore. That's the thing we're trying to prove. Always be on the lookout for counterexamples because that will help you determine whether or not we found the argument's just invalid to begin with or it's valid but unsound. Okay, so here is the argument. So let's see if it's valid first. So all birds can fly. Okay, cool. Assume that. Assume that bats are birds. Okay, cool. Therefore, bats can fly. Does that seem like a valid argument to us? Do the premises imply the conclusion? In a world where these things are true, do we get that this is true as well? I think so. I can kind of, again, plug in bats into this statement and get out that they can fly. That makes enough sense. So it seems like a valid argument, but is it a sound argument? Why not? That is correct. It is unsound. What's going wrong? We have premises 1 and 2. Is 1 a true premise? Is it true that all birds can fly? No, you have like penguins, right? Penguins are birds. So this is where it goes wrong. And I'm not actually sure if bats are birds. Are they? We can look that up on Wikipedia. But I'll put a question mark next to that. They might be some weird species that has nothing to do with birds. Who knows? But maybe they are. But either way, premise 1 ruined our day in terms of soundness. Yes? So this cannot be a sound argument because this is not a true premise. Okay? So we found a counterexample, and that showed us that it was not a sound argument. Okay? Any questions about this example before I have you guys get into groups and try your own? All right, I have a bunch. So let's try the first one. Please get into your nice little peer instruction groups, introduce yourselves, and take a couple minutes to try this one. See if this argument is valid or sound. So here, again, are the first 2 premises, and here is the conclusion. So give that a try, and then enter in your answer, please, while you're thinking about it, on the ByClicker page. Why did I do that? There it goes. So, enter in your response. Give you like 2 minutes, okay? Give it a try. Is it valid or sound? There. While you're working, I'm going to look up bats on Wikipedia. They're mammals. That means they're not birds. Wow. So both premises are false. How cool. Take your time. Take like 30 more seconds to get an answer in. All right, I think that was enough time. Let's see what we're thinking. Boop. All right, we think A is the answer, with a majority, it seems, at least of the people who responded. So let's take a look. Let's see if this is valid. All right. All cats are mammals, and so are bats. So we're assuming this. Assume all cats are mammals. Assume all dogs are mammals. Does that tell us that cats are dogs? No, it doesn't follow, right? There's no way that I could go from those two together somehow, in some combined form, question mark, to prove this, right? I know that they're both mammals. I don't know that a cat is a dog or a dog is a cat, though. That's not enough information. That's extrapolation. That's not based on the premises. Does that make enough sense? Because that means it's not valid. It can't be valid. Assume this is true, assume this is true. Somehow use that to prove this. It doesn't follow. Okay? I hope that makes enough sense. So this is out. We cannot make it valid. So that means it can't be sound, right? In order to be sound, it must first be valid. So that knocks that off. Well, this was also always impossible, right? It's only A or C, right? And then that leaves us with neither. This is just a bad argument, right? It's neither valid nor sound. Does that make enough sense? That we noticed that we needed these to somehow come together to prove this, and it didn't. Maybe how would we have to change one of these premises to make it true? So maybe we could say that we could change this one to say all mammals are dogs. If we change that to that, then it would make sense. We wrote all mammals are dogs and all cats are mammals. We could use that fact to get dogs out of every possible mammal. So yeah, this isn't enough information to conclude the conclusion. Does that make enough sense? All right, so the answer is in fact D. So pat yourself on the back if you were the two groups that got that. All right, let's see about the next one. So give this one a try. You're already introduced to each other, so I'll give you less time. Take a minute and a half. Try this one. You have, again, two premises and a conclusion. I'm purposefully giving you hard questions. Why don't I get a start? 30 more seconds. Okay, let's see what we're thinking. And show results. All right, so either A or D. Interesting. Still a majority, says A. So let's take a look. Premise 1 is telling us if someone was a philosopher, then they weren't a historian. Okay? Premise 2 is saying Socrates wasn't a historian. And then we're concluding that, therefore, Socrates must have been a philosopher. Okay. We think that this is valid. So let's see. Let me introduce some hand-wavy symbols that might help us see the truth. So this is trying to say if someone was a philosopher, then they weren't a historian. You can conclude that. So it's like, you give me a philosopher. You give me proof that somebody was a philosopher. And I'll give you proof that they were not a historian. Remember that symbol? Not. Okay, so it's kind of saying, you give me a philosopher, then I'll give you the fact that they weren't a historian. So you can go this way, right? From left to right. And then we're saying Socrates wasn't a historian, and we're trying to conclude that Socrates was a philosopher. Okay, so we have this proof right here. We have not historian, right? Something like that. And then we're trying to plug that in to here and see if it gives us the fact that Socrates was a philosopher. But again, this is not enough to prove this. So it is, in fact, neither. One more time. Look at the direction. If someone was a philosopher, then they weren't a historian. You're trying to go, with this one, assuming this, you're trying to go backwards from not historian to philosopher. That's not the way that arrow's moving. Does that make sense? You can't go in the opposite direction. That is not correct, logically. And we'll talk about that when we get into some symbols. Does the arrow help us see why that is not valid? Any questions about that? That's weird. That kind of goes against some of our intuition. And that's why we're teaching you logic in this class. Any questions on why it's neither? It can't be valid, so that kicks off all of these. So it's neither. Okay. Any last comments about this one? I have one more for you to try. I believe in you. Okay. Again, one last one for you to try. 2 premises, 1 conclusion. All computer scientists like to dance salsa. Some men are computer scientists. Therefore, some men like to dance salsa. Give this a try. Take your 2 minutes again. Valid sound both or neither. Draw arrows. That might help you. What do the arrows lead us to? 45 more seconds. All right, have we got an answer in? Seems like we've quieted down a little bit. 13 more seconds. All right, that's time. All right, we're either thinking A or C. No neithers this time. Interesting. So we think C with a slight majority. I think there's more than, this is by group, that's okay. There's probably 11 groups, so that makes sense. So, slight majority think invalid and sound. So let's see. Let's take a look. Let's draw the arrows, because that really is logical, even though it sounds a bit hand-wavy. So this is saying all computer scientists like to dance salsa. So you give me a computer scientist, and I'll give you someone who dances salsa, because those are one and the same. Go in that direction. Yeah, kind of what you can conclude. That's what the first premise is saying. And then the second one is saying that some men are computer scientists. So you give me not every man in the world, but some men. I'll draw a dotted box. I don't know. Give me a man. And then I'll tell you that some of those people are computer scientists. We can conclude that. Okay? So that's kind of the direction you can go. And then the question is, does that follow, or does this conclusion follow from those premises? Therefore, some men like to dance salsa. Does that seem like a valid argument to us? Yeah, kind of like, if you know the word transitivity, this is a transitive kind of relation, because you can like plug these middle bits in and lead that from here to here. You have CSCI, so some men are computer scientists, and every computer scientist likes to dance salsa. You can chain those together and get that some men like to dance salsa. Okay, so it's definitely valid. Nice. Now, the question is it also sound? So what does it mean for it to be sound, right? It means that both of these have to be true statements. So are some men computer scientists? I would say that is true. But about this one, is this true? All computer scientists like to dance salsa. Every one of them. I have a feeling I'm in the minority. I enjoy salsa, but I don't think all my other computer scientist friends love it. So this ruins the party as far as soundness is concerned. Okay? So, cannot be sound, cannot be neither. It's only valid. Any questions about that? It is not sound because this is not a true statement. We good? Okay. So I drew these silly little arrows to have to do with like an if-then relationship. Let's like spell that out in logic. Let's understand what that means, really, so that we'll never make any mistakes again, okay? Once I give you this little section, you will never fall for this trick again, okay? So let's talk about implication. That's the logical if-then statement, if-then block in Scratch, okay? So again, we're going to logic because English, we remember, is ambiguous. We would like to spell out one way of interpreting the word if. All right, so let's do that. Let's come up with a truth table for an if-then relationship. All right, and I want you to think of it in terms of when it could be false, when an if-then relationship could be false, because false, remember, that's easy to think about when we're coming up with these truth tables. I want you to think about falsehood as you were lied to by somebody. That's what it means for something to be false. You were lied to. Sad day. So here's my silly example. So dad says, I will give you $20 if you mow the lawn. Okay? So this is the condition under which you get $20, right? And now we want to ask the question, when would we feel cheated if we didn't get the $20? Okay, because it's like, if this is true, then this is true. So there's like an arrow going that way. We see that? And we're going to come up with when that should be a true statement, given all the options, based on this fact. Under what conditions would we feel cheated, would we feel lied to, if we didn't get $20? Because that'll tell us when the if-then statement logically would have been false. That'll tell us when the if was false. Okay, so here are the possible universes, all the different options of you mowing the lawn and getting $20. Okay, they could both be true. One of them could be false. They could both be false. And now we ask the question in each case, do we feel cheated about what Dad told us before? Okay? So, case 1. You mowed the lawn, and here it is. It's like an if-then statement going this way. So, logically, it looks like this. This is our if statement. So, if this is true, then this is true, right? If we mowed the lawn, then we get $20. That's what Dad is telling us. If we mow the lawn, then we get $20. So, case 1. True, true. Do we feel cheated? Do we think that Dad lied to us when he said, I'll give you $20 if you mow the lawn? The answer is no, right? Because, I mean, we mowed the lawn and we got our money. That was the deal. It seemed to have been upheld in this case. So this is fine. This should be a true part. Okay, this should be true. What about this one? Well, actually, let's come back to that. The rest of these are called the vacuous cases, if you care about learning a new word. But these two are interesting in that the statement was, I will give you $20 if you mow the lawn. So if you mow the lawn, then I'm going to give you $20. Here are the cases where you did not mow the lawn, right? So here's one, did not mow the lawn, but you ended up getting $20 because Dad is a nice guy, okay? So do you feel cheated? Of course not. You got $20 without doing any work at all. So that's not false still, right? Same with this one. You didn't mow the lawn and you didn't get $20. You're not cheated because you didn't uphold your end of the bargain, right? So again, this is not a false part of the logical if. This is the one case right here where you feel cheated, right? If you mowed the lawn, but you did not get $20. Does that make sense? Why this is the one case where you were lied to, where this was not a true statement. If you mow the lawn, then I'll give you $20. You feel cheated in that one case and that one case only. Yes? And so that tells us that this is where it should be false, okay, when we make a logical if-then relationship. Okay? So with that, we can make a new symbol. Why not? And it's called implication, is the fancy term. It's saying, it's how you express if A, then B in math. And really, you think about it as, if A is true, then B is true. But doesn't really matter. This is kind of implied anyway. Okay, so implication is the logical term for an if-then statement. You have this double-barred arrow kind of thing, and you put what's the condition on the left, that's the if part, and then you have the then part on the right. Okay, that's the idea. So if this was like mow the lawn and this was get $20, this is how you would write if you mow the lawn, then you get $20. A arrow B. A implies B. We write it. Okay. Oops. This is if, and this is the then part. All right. And yeah, in programming, we call it a conditional statement, right? We know about that now, like an if-then block. And we just notice what the truth table should be for this if-then logical form. Okay. That's what we want. So every case it's true. It was a true statement to say if A, then B. Unless you're in this one case, right? If A was true, like you mowed the lawn, but B was false, like you didn't get $20, that means the if-then statement was false. That means you were lied to, okay? You can also think of it as in terms of like something like this, like if I give you A, then you have to give me B. The one time that you don't is the false case, okay? Any questions about this new symbol? This new logical operation? Do you understand why it's false only in one case? And if you're trying to prove this, one day you might, you have to just show, if you're trying to prove that I'm not lying, I'm saying if A, then B, and I'm going to follow through, you have to show that it's impossible to fulfill the condition, the if part, and not receive the then part, because that's the one false case. You have to prove that you're not in that case for that to be a true statement, right? Okay, so that's implication in a nutshell, and that will help you with these kinds of deduction proofs, okay? Why seeing if something is valid, it's very easy if you start drawing arrows, logical arrows, okay? So the reason this is a valid statement, at least, is because we can convert this to logic, okay? This follows, it's valid, it follows from the truth table for all this stuff, okay? And I'll show you why. Follows from the truth table for colon. All these, because the first one is saying all men are mortal. So if you're a man, then you're mortal. You see that? You can translate it into implication. If this is true, if man, then mortal. Yes? And so remember what validity is trying to do. Like, assume that this is true. If this is true, and this is also true, then this must be true down here. Mortal is true, right? All that stuff. Just attach that at the end. And this is a valid argument. It is true because we can just draw the truth table for implication and make the A bit man. Like up here, this can be man, and B can be mortal, and this can be man implies mortal. And this is a true, oops. And this is a true statement now. This whole thing, this can be concluded that we're in the true case because of this. If we assume that man implies mortal is true, we're assuming, right? Let me use a different color for fun. We're assuming, because it's true, we're in one of these three cases. Yeah? That's what it means to check for validity. We assume that the premise is true. Try to prove the conclusion. So we know we must be in one of these cases, because those are the only true cases for the implication. And then, again, we can just read off the answer of the table. We're also assuming that man is true. So the A part, the hypothesis, we say. We're assuming that that was true. So, dun, dun, dun. There's only one case where this is true and A is true. It's that first line. Yeah? It's just this line right here. Because A is true, and so is A implies B, and that's what we're pretending, like A is mortal, or A is man, and B is mortal. Something like that. We have just whittled off all of the possibilities down to just one, and in this one case, oh, yeah, B, that conclusion, is also true. And that is how we can just read off of a table that it was a valid argument. Does that idea make sense? Just figure out what case you must be in using a truth table, now that we took so much effort to come up with one. And then it's all logical and beautiful. We don't have to do anything more. Any questions about that? So this is immediately valid based on what we know to be if. Any questions on that? All right. Yeah. Let me check the time because I lost my. I can just check it here. Okay, we're good. Let me see what I want to do. Okay, no new essay. That's good. All right. So another thing that you might ask is, okay, I told you that computers are so good at deduction. Does that mean we can make a circuit that figures out whether or not an implication is true, an if-then statement is true? And the answer is, of course, yes, you can. So something like, okay, take a wire for A and a wire for B and do some fancy magic with circuits, question mark, and somehow get out the result of A implies B. Can we do that? Yes, we can, because remember that I told you that you can build any circuit out of and, or, and not, right? Remember that? It turns out that implication is equivalent to not A or B. Beautiful. And that'll end up with all these rows being the exact same. They're equivalent. Just add one more. And so that's how we can make a computer check the answer for us. And let's do this, just to remember our logical operations. So what is not A or B in this case? So A is true, so not A is false. ORed with B, anything ORed with true is true, right? So that matches, true. All right, not A or B for this column. So not A, so not true, that's false. So false ORed with just B, which is false. Oh man, that's the one time it's false for an OR. Isn't that fun? So it is going to follow from all the rules that we know that this is an equivalent statement. And then this is not A ORed with B, so negate A, make false true, or true with anything, you've got true again. True. And then again, negate A, make it true, or it with anything, it's going to be true. And so they really do match up, and you can make a circuit that does that checks if an implication is true. Isn't that nice? Any questions about that? Let's bring it back to computer science, as I think I'm required to do. Okay, so any questions before I do something completely different? I'm going to talk about more generic arguments now. And I made a typo when I was first making these slides, and I wanted to preserve it forever. Instead of framing, I typed farming, and that was cute. So let's talk about something called frame, okay? This is when you're making an argument, probably to another human, and you're very angry, and you're like, my side is the correct side. It's obvious that I'm saying the right stuff. It makes so much sense to me. Why can't this other person understand me and see my point? Because I'm right, okay? And the answer is this topic called framing. It's short for frame of reference, right? Frame of reference is how you're thinking, how you're viewing a situation, okay? So this is more like, this is less philosophical and more like psychological, I would say, maybe, but that's okay. It still has a hint of philosophy in it. So let's talk about frames of references. So your frame, right, it's going to shape how you view the world, how you think about every little thing, okay? All the assumptions that you are willing to make, right? When you're trying to prove if something is valid, maybe you were unwilling to assume something, and you inaccurately said that it wasn't valid when it could have been, okay? So your frame of reference tells you how you think about things, which is weird. That is psychology, right? So also called your worldview, right? Your world view. And it's very hard to change somebody's worldview. Has to do with not like how you look something up in the dictionary, not the denotational definition of things, but how words have a connotation as well, right? Connotation. And I'll get into that with this nice table that I stole from somewhere. So the idea is, if you can control somebody else's frame of reference, how they're viewing your argument, then you have then controlled the argument itself, which is powerful. That's how you can get somebody to do something for you. Don't abuse that. And this also tells us why somebody can have the exact opposite viewpoint as us on a topic and then go and justify it too, which just blows my mind still. It doesn't seem right, but it always goes back to this idea of your frame of reference, the assumptions that you are willing to make. And maybe those are opposite for certain people, okay? So the obvious thing that I could use to describe all this, the best example is, of course, politics. So you can usually split a lot of people into left-wing and right-wing people. And here are very, very, very simplified views that a left-wing person might have on a topic versus a right-wing person. And the way that they frame that argument tells you pretty much all you need to know about what that argument is, doesn't it? Read a few of those and the difference. See how you can immediately conclude something based on the words that are used, the connotations that are being used? You see why you cannot convince somebody of the other side if they're using those kinds of words? So stare at that for a little bit. But that's what I'm trying to say here. That is the human element of an argument, being shaped by somebody's worldview. Any questions or comments about this? It's not really logical, right? It's more inductive, more human. Okay. All right, so enough politics for one day. Let's talk about computer science again. Are there any questions before I move on to one last topic? And then you can have time to work. So, I would like to talk about a very fun way of thinking about a problem. If you can turn it into something called a state machine, then it makes it very easy to think about something and to break it down. So I'm going to try and answer this question. I'll give you one example of a way to break down a computational process into something that you can think about and understand, right? So normally, like the general term is, how do you come up with an algorithm to do something? Yay. So algorithms. And how can I break it down? How can I break it down into little tiny steps that I can do this, then this, then this, and then that will give me the goal that I was trying to get, right? I'll draw that in rainbow, because why not? Okay, so here is one way to do it with something called a state machine, okay? If you can find a state machine for what you're trying to do, and you can draw it out, then it's very hard to make an incorrect program based on it, which is awesome. So yeah, a state machine is just, it's really a diagram, and it's a way to abstract away some certain process that you're trying to perform. So I'll zoom in on this in just a second, but you're always in, the idea is you're in a state, or your program is in a state when you're inside of a state machine, and you can move along between states using things called transitions. Oops. Those are the arrows that take you from one state to another. And sometimes you can only take one or the other based on either things like input or time of day for this case, maybe. So here's a state machine that like models a person, a very simplified person. Usually you talk about the starting state and you draw an arrow to that. Like, let's say that this is a starting state. That is where we begin our existence at home. Okay, so we're a person, we're in a state machine, and we start out in the home state. Maybe it's like, it's the morning, we've already woken up, so we're at home, and then it's time to go to work, right? We need to get to this state, and there's only one way to do it, okay? That's the way that we have made the state machine. We can only go from home to work by following the take train transition, okay? That's the technical term for all of this. So we'll follow that transition, and now we are in the work state, and we can do stuff, whatever that means in terms of the program or the silly example. And once we're done being in the work state, maybe work is over, we want to take a transition out, and there's only one. We can take the train back home. Does that make sense? That's how you can model some process with a bunch of states and a bunch of transitions between states. Okay, so now we're back at home. Maybe it's nighttime, and then we have to sleep, and we could wake up again. So sleep takes us into the bed state, and waking takes us back into the home state, apparently. Maybe it's the weekend, so we can go around in this one state without going to work a few times, right? It's a long weekend. And then we could go back from work to home. Maybe we forgot something at home, we need to go back without having to go into the bed state, right? You could follow these transitions in any order, but you have to follow them in that way, right? Any questions about that idea? It's kind of simple, right? It's not too bad. It's just you got a bunch of states and a bunch of ways to move around between the states. The hard part is coming up with a state machine for the problem. Okay? Any questions about that one or this? Oops. How about this one? And then I'll show you a really cool example for the last slide. A very important one. Okay, so here's like a state machine that models like somebody and the driver involved in like an Uber transaction, or like somebody's ordering a Lyft as well. So like maybe here's your start state. The user requests a trip, and then in order to assign a driver to the person who is asking to go somewhere in Uber, they have to get a payment from them, right? You got to check their credit card and make sure it's going to work. And so they request a payment. Then you're in the payment state. Either that payment failed or succeeded. So if it succeeded, you can assign a driver. If it failed, you got to go back and try a new credit card or something. So you can see how this might get complicated very quickly, but it keeps you honest about where you can be inside of your program. That's what a state machine is very good at. It's like you have to make a payment, and it has to succeed until you can have a driver assigned to this user. Yeah, that's the key. All right. So, and then once the driver gets assigned, the person's going to come pick you up in their car, and then you're going to go somewhere. And then eventually the trip will be completed, right? You're going to be dropped off, and you get out of the car. And then as far as the driver goes, they're back in the unassigned state or something. And then that is the end of the trip. Okay, something like that. That's an immediate transition you can take. But yeah, just a bunch of states, a bunch of transitions. And they can guarantee things like, oh, you had to pay before you can get in someone's car, right? Any questions about that idea? It's very powerful, the state machine. All right. So here's another silly example before a cool computer science example. So the trick, let's make our own state machine finally. The trick is you got to group your program, the ideas of your program, into states and then actions that you could perform inside of those states. Okay? So let's make a state machine for you as a student. Okay, a very simplified one, of course. But maybe like as a student, I think of you as a two-state machine. You have two states. You have a learn state and you have a practice state. Right? I'm trying to get you moving between those a lot of the time. So when you come into the class, you have nothing to practice yet. So you start out in the learn state. That's your initial state. And then at the very end of the semester, when you take the final, there's nothing else for you to learn. Your last state that you'll end up in is called the practice state, right? That'll be that one. And so you specify the starting state with an arrow coming from nowhere, and then a ending state. There could be multiple with like a two lines instead of one surrounding it, two circles instead of one circle. That's called a final state. And so your final state will be practice, but your starting state, your initial state will be learn. And then like you alternate between the two states when I ask you to do things, right? Or class starts up again. So you learn, I assign something, that's this transition. Then you practice as long as you can while the assignment isn't finished, things like that. You can stay in a state. Like you can take a transition that keeps you in the same state. Does that make sense? As long as you're not done, you can stay in it. That's totally fine. Then, like, okay, you're done practicing. It's time for lecture again. It's 4 o'clock on a Monday or a Wednesday. And so we'll go back into the learn state. Yeah? And then you can stay in the learn state while the lecture's not over, hopefully. And that's how you'll move around, right? Boop, 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 boop. And you'll take those transitions in that way. Any questions about this silly example? It is a state machine. You can be modeled as a state machine. All right, I have one last example of a state machine that will build up together, and it actually does something cool in computer science. Okay? So this was actually an algorithm that I was taught in my very first computer science class that I took at Fresno State. So, and I'm passing it on to you. Here's how you can count the words in a sentence, in a big, long sentence of characters using a state machine. Okay, and it very much simplifies this whole process, because think about the algorithm without a state machine, it will get very complicated. Okay, so here is the idea. We are going to like ask somebody to enter in a sentence, right? And maybe we're going to do it in Scratch, so it's going to be saved into the answer variable. And here's what we typed, maybe we typed like hi mom. And the naive way to count the words is like count how many spaces. Let's just throw that off immediately, like space hi, space mom. So it's a harder algorithm, or it's a harder topic than you might think. And so there's my input where those symbols mean a space. And we want to count and notice that there are only 2 words in the sentence. Okay? And so let's figure this out. The trick is, the key idea, the way that this is going to work is we're going to read each character one by one. We're going to go through this answer, call it a string, right? A string of characters. And we're going to look at each character left to right. And notice if it's either a space or not a space. Okay? Because spaces are going to give us the answer, just not in the count of each of them way that you might think. Okay? So the key idea is that white space, any space character, like when the user presses enter is just as good as pressing space, right? Or tab. White space separates words, and each character is either part of an old word or the start of a new word. Yeah, when we're counting them. Like we don't want to see the H and like, okay, new word, and then see the I and say, oh, that's a second word. No, it's part of the same word. So this is going to be the algorithm. Okay, we have 2 states. We're either outside a word or we are inside a word. And please yell at me if this stops making sense. But these are our states, and we're going to start in the outside a word state because we haven't seen anything yet. Okay? And we're going to go through each character of our answer, of the thing that we're trying to count the words of. and look at each individual character from left to right. Okay, that's going to be our input to our state machine. That's going to allow it to transition. Woohoo. So here is how it works. And hopefully you'll see the logic of this, and then I'll give an example of why it works with this example. Okay, with this answer variable. So you start out outside a word. We haven't seen any words yet, unfortunately. And, well, the second you see one, right? The second you see a word, you know that you have a new one. Does that make sense? The second you see a word, you're now inside of a word, yes? Because you've seen a word character. What does that mean in terms of transitions? This doesn't put us inside a word. That's still outside of one. But it's a non-space. It's a non-space that brings us inside of a word, okay? So see a non-space character. That will bring us into a word state. And so that's like us seeing the H. That brings us into the inside a word state, yes? And then we're going to look at the I next, right? We're still inside of a word, aren't we? So we're going to use that transition to stay inside of the word state if we see still a non-space character. See non-space. Because that will keep us inside of the same word, okay? And I won't try and count other ones, okay? I'll talk about counting in just a second. Let's just get this state machine working first, and we'll see why it helps us count. And then, okay, we were inside of a word, inside of a word. What brings us outside of a word is the space character, right? Some white space character. Boop. So if we see a space character this time, see a space, or a new line, or a tab, or whatever, that'll bring us into the outside of word state, yeah? And we remain outside of a word as long as we keep seeing spaces, yes? So we'll use that to stay in this state. See a space. And now the algorithm kind of falls out pretty naturally. Just keep a count variable for all the words that you've seen. Start it at 0. And which of these transitions should increase our count? This one, this one, this one, or this one? What do we think? When have we seen a new word? And we should add to our count of words. Yeah, I think I heard it's this one. Does that make sense? The second you see a non-space character having been outside of a word, going into a new one, right? You go from outside to inside, you have just seen a new word, +1. And that will correctly take care of like weird spacing issues and count the words in any sentence. Isn't that cool? So let me show you this working. I'll use my, I'll just stay in green, I guess. But let's go through all the characters of this string and see how this state machine correctly counts the words in it. Okay, there are 2. So we initially start in outside a word state. That's our initial state. So we're here right now. We're outside a word. We see a space. And so we just remain. We take this one transition we can take, right? We stay outside of a word. Yeah, we're still over here on the left. We saw the first character. Now we look at the H character. That lets us, because we're in this transition, right? We see a non-space character. There's only one transition we can take. That brings us inside of a word. So we're here. And also we increase our count. So count becomes 1. We just saw one new word. Okay, so now we're here. And we look at the I character. That is still a non-space character. So that's the same word. We stay in the inside of a word state. All right, then we see a space. Oh, that brings us to outside of any word again, right? We're done with this first one. We're now in the ether. We're not sitting inside of any word again. So we saw a space. That brought us here. And we saw another space. That'll keep us in the outside of word state. Ooh, that doesn't double count or anything. That's nice. So that was our second space. Kept us there. And then this M will bring us from here to here. And that will correctly see that second word once and for all, transition us into the inside of a word state, and we have 3 more non-space characters, so we'll just stay inside of that state until we're done with the string, okay? So we just see 1, 2, 3 more characters, the O, the M, the exclamation point, inside of a word, never going back to outside of a word, and never adding another number to our count, okay? Do we see how that's going to count the words in any string of characters? Isn't that cool? It's very simple. It's a 2-state machine, And it's not too hard to program once you've learned about if-then blocks and variables. Isn't that fun? So any questions about this? This is the cool example that I promised. State machines are useful. They're very hard to get wrong once you've spelled it all out like this. Okay. So if there are no questions, that's all I have for us. So no new essay this week. I'll give you a new programming assignment after Wednesday's lecture, but not today. So you are free to work on whatever is assigned that you need to work on in the remainder of class. If you're done, you're free to go. And I'll, of course, be here to answer your questions.